Okay, welcome back. Let's now start our section 9.2, which is hypothesis test for population mean with standard deviation known. So the population mean standard deviation is going to be sigma. If this is known, then we're going to have something called z-test because we're going to rely on the z-score. Then it is a statistical test for the mean of a population. It can be used either when n more than 30 or when the population is normally distributed. And another thing is we require sigma is known. Then it is also related to the sampling distribution of x bar. So this is actually the z-score of that sampling distribution. So x bar minus the mean of the sampling distribution with the original mean mu divided by sigma over square root of n, which is the standard deviation. So, and we call this the test statistic. And then we do have some assumptions for this z-test for mean when sigma is known. The sample is a random sample and either n greater than or equals 30 or the population is normally distributed. Okay, so now let's follow through the steps. So step 1, we're going to state the null and alternative hypothesis. And we're going to have one example to state out the whole process. Consider the following example. A food company produces bags of peanuts weighing 336 grams. Periodically, the quality control department takes samples of peanut bags to determine whether the packaging process is under control. That is to decide if the average weight of the bags has changed. A random sample of 40 bags is taken from the production line and has a mean of 330.91 grams with a population standard deviation. A population standard deviation of 11. So we know sigma equals 11. Population standard deviation known. Has the average weight changed at alpha equals excuse me. Has the average weight changed at alpha equals 0.05? Now we have two possibilities. The average weight of the bag is 336 grams, or the average weight of the bag is not 336 grams. So now we kind of get a feeling which alternative we're gonna use because we have three scenarios. Does not equal, more than, or smaller than. So this is probably a does not equal problem. Then we can say the average weight of the bag is not, so mu equals or mu does not equal, and then we're gonna set up like this. So the null hypothesis H naught mu equals 3, 3, 6, and a alternative H1, which mu does not equal to 336. And there are two hypotheses in the hypothesis testing. The null hypothesis H naught, this is hypothesis assumed to be true throughout the test, assumed to be true, and it always contains equals sign. So this one you just put equals, and then the alternative one we have to look at the claim. So has the average weight changed? So changed. So it's not that number anymore. Of what? 336, and that's why we set it up this way. And step 2, we want to find the critical value. So from the example, since alpha equals 0.05 and the test is two-tailed, the critical value is a positive 1.96 or negative 1.96. So why we say that? So two-tailed or two-sided test means your alpha will be equally distributed to two sides. So this is alpha over 2, and this is also alpha over 2. Since we know alpha is 0.05, so then we got 0.05 divided by 2, that's 0.025. So that leaves us this number going to be z sub alpha over 2, and this number going to be negative z sub alpha over 2. So critical values separate the distribution with a empty area, which we call it non-critical region, and then the shaded area we call it rejection region. So now based on this alpha divided by 2, we read the table z sub 0.025, that's 1.96, and then that's negative 1.96. So standard normal table. So let's check again, 0.025. So if we want to check 0.025, we're going to go to the left side because this is cumulative to the left. So to the left means 1 minus 0.025, that's 0.975. 0.975, that's 1.9 and 6. So we write down 1.96. So any test statistics less than this negative 1.96 or more than 1.96 will be rejected. So now we can compute the test value. So from the example, we know the null hypothesis, which is mu equals 336. The alternative hypothesis is mu does not equal 336. We also know the x bar, which is 330.91, sigma equals 11, and then n is 40, the sample size. Then when we assuming the null hypothesis is true, then this mu equals what? When we assume that's true, then this mu equals 336. So we have all the information here. X bar 330.91, mu 336. 11 divided by square root of 40, so all plug in, and then you calculate that value to be negative 2.93. Negative 2. And then we need to make a decision. When making the decision, there are only two possibilities. If your test statistic falls within the critical region. So the shaded area we have here is the critical region, or we call it rejection region. So fall within that region means even more extreme from the critical value. This negative 2.93 is even smaller than negative 1.6, and then it lies within the rejection region. So we're gonna say we reject it. If it's here, then no, we will not reject such value because it's not in the rejection region. So we say since negative 2.93 is smaller than negative 1.96, the test statistic falls within the rejection region. The decision is reject the null hypothesis. But now yet then, we have to make a conclusion to summarize the results. So for conclusion, there are only two possible conclusions. If you reject the null, then there is enough evidence to support the claim at your specific level of alpha. If you fail to reject the null, then there is not enough evidence to indicate the alternative is true or to support the claim at your specific level of alpha. So conclusions always written in terms of the alternative one. So in this example, we rejected H0. That indicate there is enough evidence to conclude the average weight of the peanut bags is not 336 grams. So so this is actually the claim. We have enough evidence to conclude the claim. Don't forget this one, at a specific level of alpha. So at alpha equals 0.05. At the type 1 error, the tolerance for the type 1 error is 5%. And then we call this whole process the critical value method. Then we can actually calculate something called p-value. So the p-value or probability value is the probability of getting a sample statistic, such as a sample mean or a more extreme sample statistics in the direction of the alternative hypothesis when the null hypothesis is true. So a more extreme setup. So we have the decision rule when using p-value. So when we calculate that probability to be small, so smaller than what, type 1 error, then we say we're going to reject the null hypothesis. If that p-value is more than the type 1 error, then we fail to reject the null hypothesis. For the full company example, p-value equals the probability of d smaller than negative 2.93. So why we say that? To capture that probability, we can draw the normal curve. Here's a 0, and the z-score we have is negative 0.93, the critical value. So we want to know the p-value. P-value means more extreme. So we want to know from this point lower, but since it's a two-tailed test, then we have also the probability here. So add up those two parts together, give you the p-value. So since symmetry z, they're the same, so you use 2 times the probability of z smaller than negative 2.93. So you got 0.0034. Then we can use the p-value method to make the decision. P-value equals 0.0034, which is smaller than alpha, the type 1 error. Then the probability of that happen is very, very low. And then we definitely gonna say we reject the null hypothesis. Okay, let's look at a practice problem. The average wage in 2009, the average wage in North Dakota was $45,218. A researcher claims that the average wage has increased since then. So we're going to mark all those important information. So this is one, and then increased. And to test his claim, so the claim is more than that, right? Increased. To test his claim, he takes a random pool of 36 workers in and find their average wage to be the sample mean 46,615 with a population standard deviation of $7,513. Test his claim at type 1 error rate 10%. So alpha equals 0.1. Then we're going to set up like what we did before, right? Step 1, we're going to state the null and alternative hypothesis. So we can just write down the null hypothesis. So actually for this chapter, we pretty much only look at the population mean as the parameter to do the hypothesis testing. So it always have this mu represent the mean. And since it's a null hypothesis, we know it always includes the equals sign. So mu equals, and that's more like fixed. Equals what? You actually get it from the claim. So a researcher claimed that the average wage has increased since they get this number, so more than that number. So the target number is 45,218. So the null hypothesis will be equals that number. And the alternative hypothesis will be mu increased, right? So that's more than 45218. So this more than sign tell us is a one-sided test. It's right-tailed test. Right-tailed test. And then step 2, we're gonna find the critical value. So like we did before, we're gonna find the critical value. So this is based on the alpha and the sign you have for the alternative hypothesis. Find the critical value. So we're gonna write down our alpha equals 0.1. So it's given from the problem, always given. Don't worry about this. Alpha. And then we know we're looking at a one-sided test, or the route tail test. Then we can find the critical value by drawing this normal curve. So we have this curve, the mean stands for the standard normal, the mean is 0. We're looking at the rejection region because it's right-tailed, so the rejection region is going to be from the right. So we're looking at one value that to the right you have alpha because it's one-sided, right-tailed. So all the taper arrow will go to the right side. So you have the alpha equals 0.1. Then this value is going to be z sub 0.1 because you're looking at a value to the right. You have alpha, which is 0.1. So this is z sub 0.1. So that is check the standard normal table. With 0.9 inside out. Inside out. Why we check 0.9? Because to the right you have 10%, to the left you have 90%. So we go find the 0.9. Where is that? Oh, it's right here. 0.8997, 0.9015. So in between. So we read that as 1.285. So this is 1.285. That's the critical value we have. So critical value means you have a critical region. So to the right. That means we're going to reject the null hypothesis if the test statistic you calculate, we use z represent that z-test statistics. Reject h0 if z is more than, even go more extreme than this value, 285. 1.285. Then let's see what we can do. Step 3, calculate the test statistics. So it's a z test statistics equals x bar minus mu naught over standard deviation over square root of n. So do we have x bar already from that? Yes, we have 46615. Minus mu naught. Mu naught means we find the mu given from h naught. So 45218. Divided by sigma, which is 7513 over square root of n, which is 36. So now we're going to obtain that value using the calculator. So open parenthesis, 46615 minus 45218, close parenthesis, divided by, again, 7513, open and close the parenthesis. 7513 divided by 6 because square root of 36 is 6. Okay, we got 1.1157. That's the test statistic. That's step 3. And then step 4, we're going to make the decision. So we can look at a curve. So 0 is right here, and this is alpha, which is 0.1. So this number is 1.285, and 1.1157 is somewhere here. So it doesn't lie within the rejection region. So our test statistic equals 1.1157. We reject it if it's more than 1.285, but it is not. 1.1157 is not more than 1.285. So we fail to reject. Fail to reject H0. And then the last one will be step 5. Conclusion. So we're going to say there is, so the conclusion is based on whether you reject or fail to reject. If you fail to reject, then you put there is not enough evidence to conclude the claim. What's the claim? To conclude the average weight has increased. Not yet. We need to specify what significance level at alpha equals 0.1. So this is a conclusion. There is not enough evidence to conclude the average weight has increased at alpha equals 0.1. And that's all for the critical value method of the 5-step hypothesis testing. And one last thing we can look at is the p-value. So we can always go with the p-value method. So the p-value method, you don't really look at the step 2. We don't need to find the critical value. We are gonna first calculate the test statistics. Then we know z equals 1.1157. And then we're looking at a probability (1.1157) or more. So we want to know this probability, the shaded area. And then actually we want to calculate 1 minus the probability of z is smaller than 1.1157. So if we can calculate that, then the value is obtained. So you got this area, which is 1 minus the shaded area. So now we can know the probability. That's going to be 1 minus probability z smaller than 1.12 because you want to round to 2 decimals to use the table. 1.12. 1.12 is right here. 0.8686. 1 minus that. 0.1314. So probability of, okay, so we have to write this. So we're actually looking at probability of z more than 1.1157, and then that is 1 minus probability of z smaller than 1.157, and then we calculate it to be 1.1314. So since the test is a red tail test, so this sign is from the H1. So alternative hypothesis, we have mu more than something. So more than, that's why we look at probability of z more than. So to the right side, because it's red tail test, to the right side to find the probability of that number or more extreme than that. So probability d even more than that critical value. We got a p-value equals 0.1314. So that is more than alpha, which is 0.1. So from the p-value method, we know we failed to reject. Failed to reject the null hypothesis. Hypothesis. And what if we have a smaller than case? Then this is going to be probability smaller than 1. And then two-sided, we already seen that probability 2 times probability of z smaller than the left-sided value. So that's all for section 9.2.